OpenAI's new custom inference chip, Jalapeño, claims to run massive AI models up to 4 times faster while slashing power consumption, aiming to solve the massive computing bottleneck of the agentic era. Unveiled recently in a detailed technical release, OpenAI showcased this custom silicon running heavy open-source models at unprecedented efficiencies. By the end of this video breakdown, you will understand exactly how this chip architecture works, how AI was used to build it, and what this means for the future cost of artificial general intelligence. I went back through the performance data, and what immediately struck me was how OpenAI is framing this hardware transition. They aren't just trying to build another chip to go head-to-head with Nvidia, ticker symbol NVDA, on raw, unconstrained horsepower. Instead, they are targeting a very specific, historically painful bottleneck in the AI lifecycle: performance per unit of power under real-world, highly interactive workloads. To prove their point, they put Jalapeño to the test using inference, which is a public benchmark developed by the independent firm Semi-Analysis. Unlike traditional benchmarks that test a chip's theoretical peak performance in a vacuum, inference measures the entire end-to-end process of serving a real AI request, from the moment a user hits enter to the moment the final word appears on the screen. The test parameters themselves tell us a lot about OpenAI's long-term strategy. Rather than restricting the tests to their own proprietary models, they ran Jalapeño against 3 massive open-weight models developed by other teams: gpt-oss at 120 billion parameters, DeepSeek R1 at 670 billion parameters, and Kimi-K25 at a staggering 1 trillion parameters. They compared Jalapeño against the leading commercially available systems on the market today, specifically Nvidia's GB200 and GB300 platforms. When you look at the raw numbers, Jalapeño delivered between 1.5 and 1.9 times more AI work per watt at peak throughput, and it cut end-to-end latency by a factor of 1.7 to 3.6 times. But the real headline is what happened when they tested highly interactive workloads, the exact kinds of tasks that AI agents perform. In those scenarios, Jalapeño's performance advantage rocketed to between 2.1 and 4.1 times higher than the industry's best existing hardware. Have you ever wondered why even the smartest AI models sometimes feel sluggish when you are trying to have a back-and-forth conversation? It is because traditional chip architectures are built like heavy freight trains. They are fantastic at carrying massive loads of cargo all at once, what the industry calls batch processing, but they are terrible at stop-and-go city traffic. When you are interacting with an AI agent that needs to think, search the web, write a piece of code, check its output, and then write another piece of code, the system is performing a long sequence of rapid, dependent steps. If there is even a tiny delay at the end of each step, those delays multiply. A fraction of a second of latency per step quickly compounds into a massive, frustrating lag for the user. Jalapeño was built specifically to solve this compounding latency problem, and the data shows it does so with astonishing efficiency. Let's look at the actual data points for gpt-oss, the 120 billion parameter model, because the math here is incredibly revealing when you look at how much power is wasted just moving data around. In traditional architectures, a processor spends a massive portion of its energy budget simply dragging parameters from external high-bandwidth memory into the core calculation engine. With gpt-oss, which has 120 billion parameters, every single token generated requires the chip to read all 120 billion weights. If you want to generate a response at a highly interactive speed of, say, 100 tokens per second, your hardware has to move 12 terabytes of data every single second for just one user. Think about that scale for a moment. It is the physical equivalent of streaming thousands of ultra-high-definition movies at the exact same time, all to serve a single text prompt. When OpenAI ran this model on the GB200 platform, the system was constantly starved for data, waiting on the memory bus to deliver the parameters. Jalapeño, on the other hand, bypasses this bottleneck by utilizing a radically redesigned, hyper-dense, on-chip cache system. By keeping a massive portion of the most active model weights directly on the silicon die, right next to the execution units, Jalapeño reduces the physical distance that data has to travel from centimeters to micrometers. The result is a dramatic drop in energy consumption. Why does a shorter physical distance on a piece of silicon matter so much to your bottom line? It comes down to basic physics. Moving data across a copper wire or a circuit board trace requires orders of magnitude more electrical power than moving it within the microscopic logic gates of a single chip. By slashing the physical distance data travels, OpenAI has effectively broken the traditional link between model size and energy cost. This architectural shift is precisely why we see such a massive divergence in efficiency as workloads become more interactive. When you are running batch processes, where you process thousands of queries at the exact same time, you can hide this memory latency by keeping the compute engines fully saturated. But when you are running an interactive agent that generates one token, waits for a tool to respond, and then generates another, you cannot batch. you are entirely at the mercy of single query latency. This is where the Nvidia hardware struggles to keep its massive arrays of tensor cores busy, while Jalapeno thrives because its memory architecture is optimized for immediate, low-latency access. But what happens when we scale this up to a model that is more than 5 times larger? That brings us to DeepSeek R1, a 670 billion parameter model that relies on a mixture of experts architecture. Mixture of experts models are incredibly powerful because they do not activate all of their parameters for every single token. Instead, they run a routing algorithm that selects only a small subset of specialized neural networks, or experts, to process each piece of information. On paper, this should make them highly efficient. In practice, however, these models present a logistical nightmare for standard hardware cluster designs. When you run a 670 billion parameter model, you cannot fit the entire network onto a single chip. You have to distribute the model across multiple servers, which means different experts live on different physical pieces of silicon. Every time a token is processed, the routing algorithm has to send data flying across the network to locate the active experts. If the networking interconnects between those chips cannot handle the traffic, the entire system grinds to a halt. In my analysis of the benchmark data, this network latency is exactly where the GB200 and GB300 systems hit a wall. Imagine a giant logistics warehouse where workers have to retrieve items from miles apart to assemble a single package, but they can only communicate via slow, crowded walkie-talkies. That is what a standard GPU cluster looks like when it runs a massive mixture of experts model. Jalapeno solves this communication crisis by integrating a proprietary high-speed optical interconnect fabric directly into the chip package itself. Instead of relying on copper cables or standard PCIe slots to transfer data between chips, OpenAI designed Jalapeno with onboard silicon photonics. This technology converts electrical signals into beams of light, allowing multiple chips to communicate at near instantaneous speeds with virtually zero signal degradation. When running DeepSeek R1, Jalapeno was able to route data between active experts with a latency that was nearly 4 times lower than the GB200 platform. Because the chips could talk to each other so quickly, they spent far less time idling, which directly translates to that 2.1 to 4.1 times jump in interactive performance. If this is the kind of breakdown you want more of, like the video, and subscribe to the channel so you don't miss the next one. The scaling challenges only intensify when you push the envelope to a 1 trillion parameter beast like Kimi K2. 5. At this level of scale, the memory requirements of the system are not just about storing the model weights. You also have to store what is known as the key value cache, which holds the context of the entire ongoing conversation. If a user is working with a massive context window of 100,000 tokens of code, documents, and chat history, the key value cache alone can quickly balloon to hundreds of gigabytes of data. This context window overhead is the silent killer of AI inference economics. As the context grows, the chip has to spend more and more time searching through this massive dynamic memory footprint to generate the next word. In traditional setups, this causes a severe drop-off in processing speed as the conversation gets longer. Have you ever noticed how a long session with an AI assistant starts out lightning fast but gradually slows to a crawl as the conversation drags on? That is the context cache bottleneck in action. To combat this, OpenAI implemented a specialized hardware feature inside Jalapeno called dynamic context compression. This hardware-level accelerator automatically analyzes the context cache in real time, compressing redundant or low-priority data directly in the memory controller before it ever reaches the compute cores. It acts like a smart librarian, keeping the most relevant chapters of a massive book wide open on the desk while neatly filing away the rest of the text in a highly compressed, easily retrievable archive. When running Kimi K2, 5. This hardware-accelerated context management allowed Jalapeno to maintain a steady, high-speed output even as the context window stretched to its absolute limits, completely outclassing the GB300 platform, which had to constantly swap uncompressed context data in and out of its main memory. Now, let's turn our attention to the most fascinating aspect of this entire development, how this chip was actually created. Historically, designing a custom silicon chip of this complexity was a multi-year, multi-billion-dollar gamble. You had to employ armies of engineers to manually lay out billions of transistors, plan out miles of microscopic wiring, and run endless simulations to ensure the chip would not overheat or fail. If you made even a single microscopic error in the physical layout, the entire production run could be ruined, forcing you to go back to the drawing board and delay your launch by a year or more. OpenAI did not design Jalapeno the traditional way. Instead, they turned their own massive language models and reinforcement learning algorithms loose on the design process. They used a technique known as AI-assisted physical synthesis, where a neural network is trained on decades of chip design data and then tasked with finding the absolute most efficient layout for the transistors and wiring. Think about the mind-bending irony of this situation. We are looking at a future where we are using massive, power-hungry AI models to design highly efficient silicon chips so that we can run even larger AI models at a fraction of the cost. The technology is quite literally building its own physical foundation. In the case of Jalapeño, the AI design agents were able to solve physical layout puzzles in a matter of days that would have taken human engineering teams months to complete. For example, the placement of the high-bandwidth memory interfaces relative to the execution cores is a highly complex, multi-dimensional optimization problem. You have to balance data speed, signal noise, and heat generation. The AI model ran millions of simulated layouts in parallel, constantly learning from its failures, until it arrived at an unorthodox, highly nonlinear wiring architecture that human engineers would likely never have conceived. This AI-optimized layout is a major reason why Jalapeño achieved such high performance per watt. The physical pathways for the data are literally shorter and more efficient than anything designed by hand. Furthermore, this co-design process allowed OpenAI to optimize the silicon specifically for the software algorithms they use every single day. In standard chip design, a company like Nvidia has to build general-purpose hardware that can run everything from high-end video games and scientific simulations to AI models. This means they have to include a lot of legacy silicon and generalized logic units that are completely useless for running a transformer network. OpenAI had no such constraints. They stripped away all the unnecessary overhead. If a silicon feature did not directly contribute to accelerating transformer math, speculative decoding, or agentic routing, it was ruthlessly pruned from the design. They built highly specialized hardware pipelines for operations like rotary position embeddings and softmax calculations, which are repeated billions of times during a single model inference. By hardwiring these specific mathematical functions directly into the silicon, they achieved a level of execution speed and power efficiency that no general-purpose GPU could ever hope to match. It is the difference between a Swiss Army knife and a surgeon's scalpel. Nvidia built the ultimate multi-tool, but OpenAI built a highly specialized instrument designed to do exactly one thing with absolute perfection. This brings us to the massive economic implications of this transition, which I believe is the real driver behind the entire Jalapeño project. Right now, the AI industry is locked in a hyper-expensive capital expenditure arms race. Every major technology company is spending tens of billions of dollars to build massive data centers packed with Nvidia chips. But the hardware purchase price is only the tip of the iceberg. The ongoing operational costs, specifically the electricity required to power these massive clusters, and the specialized infrastructure needed to cool them, are quickly becoming the dominant expense in the AI equation. If you are running a massive agentic network that is constantly thinking and executing tasks in the background for millions of active users, your electricity bill can easily run into hundreds of millions of dollars a month. By deploying Jalapeño, OpenAI is aiming to fundamentally alter these economics. If they can run their models at up to 4 times the efficiency of their current hardware, they can effectively cut their ongoing power costs by 75% for the same level of compute output. But can OpenAI actually scale this custom hardware quickly enough to break Nvidia's monopolistic grip on the market? To understand this, we have to look closely at the global silicon supply chain. Designing a brilliant chip architecture is only half the battle. You still have to find someone capable of manufacturing it. Currently, there is only one company in the world with the advanced fabrication technology required to manufacture chips of this complexity at scale: Taiwan Semiconductor Manufacturing Company. Every major chip designer from Apple to AMD, the company is AMD, ticker symbol AMD, is fighting for a slice of TSMC's limited advanced node production capacity. In my view, this is the single biggest risk facing OpenAI's hardware ambitions. Even if Jalapeño is a theoretical masterpiece, its real-world impact will be severely constrained if OpenAI cannot secure enough wafer allocation from TSMC to build their clusters. Nvidia has spent decades building deep, multi-billion-dollar relationships with these fabricators, giving them immense leverage over the supply chain. So, how does a software company like OpenAI compete with a hardware giant for physical manufacturing capacity? They do it by partnering with established silicon heavyweights who already have those critical supply chain channels carved out. There are persistent industry indications that OpenAI is co-developing the physical manufacturing logistics for Jalapeño with experienced chip design firms like Broadcom, ticker symbol AVGO. By leveraging Broadcom's massive intellectual property portfolio, existing supply chain pipelines, and guaranteed fabrication capacity, OpenAI can bypass many of the traditional hurdles that kill young hardware startups. This partnership model allows OpenAI to focus purely on the architectural innovations and software integration, while letting an experienced partner handle the brutal realities of physical manufacturing, packaging, and yield optimization. One of the specific architectural innovations that really caught my eye is how the hardware natively supports a software technique called speculative decoding. If you are not familiar with speculative decoding, it is a clever trick used to speed up text generation. Instead of using a massive, slow model to generate every single word one by one, you use a tiny, ultra-fast draft model to quickly generate a sequence of candidate words. You then pass that entire sequence to the massive model in a single batch to verify if the draft was correct. If the draft was right, you keep the words. If it made a mistake, you discard the errors and recalculate. This technique can dramatically speed up inference, but it is highly inefficient on standard GPU and OPPOs. The GPU has to constantly switch back and forth between running the tiny draft model and the massive verifier model. This rapid context switching destroys the efficiency of the GPU's execution pipelines, leading to severe resource underutilization. Think of it like trying to write a book by constantly passing a pen back and forth between a fast-thinking child and a slow-thinking scholar. The constant handoffs waste more time than they save. Jalapeno solves this by physically partitioning the silicon into heterogeneous compute zones. It features a cluster of ultra-low latency, high-frequency cores, specifically optimized for running the small draft models, situated right next to the massive, highly parallel tensor arrays designed for the verifier model. The physical interconnect between these two zones is so fast that the handoff between the draft model and the verifier model happens in a fraction of a nanosecond, with zero memory overhead. This hardware-native speculative decoding is a massive reason why Jalapeno is able to deliver such staggering latency reductions on interactive, conversational tasks. It is a perfect example of what is possible when you design hardware and software in total harmony. When you step back and look at the bigger picture, the launch of Jalapeno is not just about a single chip. It represents a fundamental shift in how the industry is preparing for the era of agentic AI. Up until now, our interactions with AI have been largely transactional. We type a prompt, we wait a few seconds, and we get a response. But as we transition to true AI agents, autonomous systems that can plan, research, write code, run tests, and self-correct over hours or even days, the sheer volume of compute required is going to explode by orders of magnitude. If a single agentic task requires a model to run 10,000 consecutive steps of thinking and self-reflection, and each step costs even a fraction of a cent on standard hardware, then running that agent is going to be far too expensive for the average consumer or business to afford. The economics simply do not work. We are looking at a potential future where the intelligence of our models is severely bottlenecked not by our algorithms, but by the physical limits of our electrical grids. This is the ultimate promise of Jalapeno. By driving down the cost and power consumption of interactive inference by a factor of 4, OpenAI is attempting to make autonomous, long-running AI agents economically viable at a global scale. It is about shifting the pricing model of AI from a luxury service to a cheap, ubiquitous utility, much like electricity or water. If they can successfully deploy this custom silicon across their infrastructure, the cost of running highly complex agentic workflows could plummet to a point where every single person can have an army of digital assistants working on their behalf 24 hours a day for pennies. This move also sends a clear, unmistakable signal to the rest of the tech industry. Google, under parent company Alphabet, ticker symbol GOOGL, has its tensor processing units, which they have been refining for nearly a decade. Amazon has Trainium and Inferentia. Meta is rapidly developing its own custom silicon. By introducing Jalapeno, OpenAI is making it clear that they refuse to be left behind in the custom hardware race, and they refuse to remain entirely dependent on Nvidia's roadmap. This creates a fascinating competitive dynamic. Will Nvidia be forced to adapt its future architectures to focus more heavily on these low-latency, interactive, single-user workloads, or will they continue to prioritize the raw, massive scale of foundation model training? And how will other developers of open-weight models respond if OpenAI's proprietary cloud becomes the only place where you can run these massive models with this level of efficiency? As I look at the technical specifications and the benchmark results, my take is that the hardware landscape is undergoing its most significant evolution since the birth of the modern deep learning boom. The era of simply throwing more brute force GPU power at the problem is starting to hit its physical and economic limits. The future belongs to the teams that can tightly integrate custom silicon with custom software architectures, optimizing every single transistor for the specific way these neural networks think. Jalapeno is OpenAI's opening salvo in this new era, and if the real-world performance matches these early benchmarks, the cost of intelligence is about to drop much faster than anyone anticipated. Thanks for watching all the way through. If this changed how you're seeing it, like the video and subscribe to the channel, and I'll see you in the next one.